Okay, we're going to look today at the inverse of the exponential, and that is the logarithm. Okay, logarithmic functions. Over the next few days, few class periods, we're going to be looking at logarithmic functions, and these are kind of neat because while there are some things that we can figure out logically, there are problems that we just cannot solve without using logarithms. So we'll look at some of the logic behind it today, but we'll also look at the mathematics too. So, all right, so let's take a look at what logarithms are. How many of you have seen or used them before at all? Okay, most of you have used it a little bit, at least. So we're gonna build on that, kind of refresh our memories as to how those work and whatnot, and then we'll look at some applications too. Okay? So, I thought it was a spider or something. Alright, well let's take a look. First of all, this is what your book has, and I'll try to condense this so you don't need to write this down. But let's take a look at how your book presents it. If x is a positive number, and a is a positive number, and a is not 1, okay, then we have the log base a of x. That's how we would read that, log base a of x. And that equals y, all right, if a to the y power equals x, all right?
If a equals 10, do you say log of 10 still? Log base 10?
If you want to, or you could just say log. Okay, we'll get to that though. So this function here, f of x equals the log base a of x, that's our basic logarithmic function. All right, and just like our exponentials, the parent function, so to speak, varied because a could be anything. Here, again, a can be anything, so the parent function is a little bit hard to define. Okay, Josh?
What is a log?
Yeah, I've never seen that.
No, as in, what's the reasoning behind calling it a log?
No.
No?
What is it? Like, for the exponent, if you have 3 squared, the squared means multiply itself by the amount of times it's squared. What is a log?
Like, what does it do to those numbers?
Yeah.
Well, a log is a function, and this is what I was going to say next. A log is a function that returns an exponent. It's kind of like you guys are familiar with using sine, opposite over hypotenuse. And then you used inverse sine. All right, well, what does that really do? Well, inverse sine, that's cosecant. Inverse sine takes that value you had gotten before and then spits back out the angle that value came from. It was an inverse. Here, it is kind of hard to define exactly what it does other than the fact that it helps us solve for an exponent. Okay? So, and let me give you a little bit clearer version of of all of this, okay? A logarithm is a function, and it takes two things. It takes a base, and it takes a value. And then it returns the exponent of the base that would give you that value, okay? Anytime you're taking a logarithm, and you say log of this equals 5, that 5 is the exponent, okay? And that's going to really be critical to keep in mind as we move forward. Logarithms give you exponents, okay? Nico?
Can I go take these? Just at 1 p.m.
Oh, you need to take that one?
Yeah, can I?
Sure, go ahead. Alright, so let's look at the logic behind this, and then we'll see how a problem that we could solve logically can be translated into a logarithm, okay? If I gave you this equation, 2 to the x equals 8, all of you, if you thought about it enough, could figure out, oh, x would have to be 3, because 2 to the third power is 8, okay? Well, to translate that into a logarithm, we're taking the log, and the base of the logarithm is the same as the base of your exponential, okay? So it's 2 in this case.
So it's a way to find the exponent.
It's a way to find the exponent,
Could
all
we
right?
then, so let's say they wanted you to graph 2x. Never mind. I'm done. Sorry.
Okay. We are going to graph these, but we're going to get to that a little tomorrow and whatnot. So, but anyways, we have the base of our exponent 2 is going to equal the base of our logarithm, okay? Now, the value that 2 to the x equals is what we're going to take the log base 2 of, okay? And then what the log base 2 of 8 equals the exponent of 2 that will give us 8. Okay? So x is the exponent of 2 that gives us 8. Is essentially what what that equation says. Okay? So it takes a little bit to kind of grip this and let it sink in, but just get that into your head that logarithms give us exponents. Now, Jacob already mentioned the common log, and we'll get to that here in a moment. But before we do, I've already used this term inverse. But let's make sure we define this clearly. Exponentials and logarithms with the same bases are inverses of each other. Okay? So, we just saw that on the previous example. Here we have a base of 2 in our exponential. Here's a log base 2 in our logarithm. Those are going to be inverse functions. Okay? So, if our function is b to the x, then the inverse of that function is going to be the log base b of the function. That'll give us x. Okay?
So it's like if they give you a certain value of y and you want to find x.
If you think about it, what the applications we did with our exponentials, you knew what the exponent was. You were trying to find the value that it equaled at the end, right? For instance, with our compound interest, you knew the rate and the time and all that other stuff. You knew that, and you wanted the value at the end, okay? Well, now we'll be able to be given a certain value and figure out, hey, how long would it take for our investment to grow to that value? Or how long would it take for, that to grow or that to decay to the specific value that we know, okay? Now, let's just look at this. We have 10 to the x equals 25, all right? So how would we undo an exponential 10 to the x?
Log of 25.
Log of 10
Log
times 25.
Hang on. We take the log base what? Log base 10, okay? And I know we don't have to write it there, but I just want you to see it. It's the log base 10, all right? And what that will do is, on this side, all that's left now is the exponent. Remember, a log gives us an exponent, all right? So then the log base 10 to 25, we would have to use our calculator for and figure out, and that would be, 1.398. And we will look at how to use your calculator to find those. But understand the concept here. Anytime you have an exponential, you look at that base, and that's going to be the base of the logarithm. Okay. Now, before we move on and look at more of these, let me just point out the fact that of how you can tell your answer makes sense. All right. Think about our original problem. We want 10 to some power to equal 25. And we can't find it exactly in our heads, but 10 to the first obviously is 10. 10 to the second is 100. So 25 is between 10 and 100. So we know that our answer needs to be between 1 and 2. Okay? So think it's really easy to punch a wrong button or to punch something incorrectly. Think about what your answer ought to be before you just go punching away, and make sure that what comes out of the calculator at the end makes sense. Okay? So we'll do more like this, but let's come over to here. We've got the log base 10 is that log button on your calculator. All right, we are going to be using your calculators a bit here, so please get those out if they're not already. Where's your locker? In Lakeside? Just look on with somebody because you'll be gone for 10 minutes if you have to walk all the way over there. Alright, so that's our common log. Then, we already looked at exponentials that have a base of e. Okay, and we saw that anytime we had continuous growth, we used e to some power. E to the RT for compound interest. Alright, so because that occurs a lot, we also have a log base e. And your calculator can do that as well. It's ln for the natural log. Remember we said e to the x was the natural exponential function? Well, the natural log is a base e.
Where is that?
It, on here,
No logs.
oh, natural log's right next to it. See that?
LN.
ln? It's above that.
LN.
Okay? Alright, so we can use both of those, and if you have the Nspire,
You don't have a bill.
it actually gives you an option to punch in the base every time. If you don't punch anything in, it automatically assumes it's 10. Okay? It also does have the natural log button there too. But even if you don't have the Nspire, we're going to learn a change of base formula that's really, really simple to help us evaluate other logs, like the log base 3 of 12 on the calculator, okay? So we'll look at that later, but for right now we'll practice a little bit with this common log and the natural log, okay? So let's do this one logically, and then we'll also figure you do it using your calculator, okay? 10 to what power is 10,000?
4.
It's the 4th, alright? Count the zeros. We have 4 zeros, it's 10 to the 4th. Okay? Now, if we were solving this with a logarithm, we would take the log base what of both sides?
The 10.
The log base 10 of both sides, okay? And even though we know it's going to be 4, go ahead and on your calculator punch in the log of 10,000. The log of 10,000. And make sure it's giving you 4. Okay?
Yeah.
Alright? Everyone get 4? I'm going to make sure you know how to use your calculators.
It puts the base automatically.
Yeah. For the Nspire, it's not going to, it'll ask you for a base, but if you don't put anything in,
You put 10.
it'll put 10 in for you. Yeah. Okay. So we get 4. Again, there's an understood base of 10 if none is shown. Right? How about this? Negative 3. Good, good. Why is it negative? Someone explain. Nico?
Because when the exponent is negative, you like you are dividing. How to explain it? So imagine like 10 squared is 100,
Mm-hmm.
and 10 to the first is 10. Then 10 to the 0 you divide by 10 again,
Mm-hmm.
and then you divide again and again and again until you get to 10 to the negative third.
Okay, good, good. That negative exponent says we're going to be dividing by that, or in other words, take the reciprocal of what that would be. Okay, so this 1,000 is typically 10 to the third. We have the reciprocal of that, so it's 10 to the negative 1/3. Okay? If we punched it into our calculator, we'd be doing the log of 1/1000. Okay? And then we get negative 3. Okay. Alright, how would we solve this one? E to the x equals 10. Before we do anything, stop with your calculators for a sec. Think. Think, yes. Before you do anything with your calculators, think. What's the value of E? 2.7. 2.718, right? Okay. Obviously, 2.7 to the first is 2.7. 2.7 squared.
It would be like
Well,
7, 8.
Well, think about it this way.
Because 3 is
It's
9.
almost 3, right?
Yeah, 3 is 9, so it's like 8.
3 would be 9,
8
and this is going to be smaller than 9, right?
in between 8 and 9.
So I know it's less than 9,
More than 8 because 2 squared.
Okay. right? So if this is less than 9, what's 3 cubed?
27.
27, okay? Now, if this were like 12, we still wouldn't be real sure because 10 is real close to both of them. But 10 is really close to 9, and even though we know it's less than 9 and this is less than 27, we could probably guess that our answer is going to be somewhere between 2 and 3. Does that make sense? So we're thinking about the value. Now, if we use our calculator, we are going to use the ln, the natural log. Alright? And what do you get when you punch in the natural log of 10?
2.3.
2.3? Okay. So, x is 2.3. So e to the 2.303 power is going to give us 10. Okay? Are there any questions? Yes.
In this type of problems, do you wanna how many decimals do you want us to put?
You know, 2 or 3 usually. I mean, if it's a large part of it, you can tell based on context. You know, if you're talking about money or something like that, maybe 2 decimal points for the nearest penny. But you know, just go based on context. Usually 3 total digits. Okay, so 2.30 would be fine. I did 2.303 instead of ending in a 0. Okay. Obviously, if the directions tell you to go to a certain number of decimal places, then do that. Okay. Alright. If you guys go into IB, or if you're part of the IB, IB always does 3 significant figures, or significant digits. Okay? Now, they'll take an answer like this, but if you rounded it to 2.30, they would take that as well.
What if it doesn't have a decimal?
Then you don't have to worry about it. You just give the integer value.
They use sigmoids on top of this? Or on this class? I mean,
Yeah.
Yeah.
Yeah, I mean, we're not as picky about it as we would be in the science class, but IB just is something to have some kind of a standard, that's what they use. So they also, they're a lot more lenient as far as simplifying, like you don't have to simplify a lot of stuff. For instance, like I would want you, if you had like 3 over the square root of 5, I would want you to simplify that. They don't care. Alright.
It's just not.
I think their thought is basically, if you're in this class, you know how to do this, so we're not gonna waste your time. But, anyways. Let's look at an application of this. Tying it together with something that we did yesterday, or Tuesday. Here we have an investment. If I invest $12,500 at 7% interest, compounded continuously, how long will it take for me to have $20,000? Okay? When you see this, how long? What are we looking for?
Times.
A time. And time in these problems is always
Months.
time in what units of measure?
Months.
Not months, it's always in years. Okay? Now, look up your formula that we looked at the other day. And see if you can't get the equation set up.
I remember this.
There, A of t equals
PE to the RT.
okay. A of t equals PE to the RT. That's what we'll use. Okay, so try to set up the equation.
We just have to set it up.
Yeah, go ahead and set it up. We'll talk about
Correct.
solving it here.
Oh.
Okay. Alright. Let's see, put it down, please.
Is it this?
I did, but I don't know what I did.
This is it.
That?
Oh, you saw it? Yeah, I think so. I remember right.
Yes.
And then what would that equal? Remember, that's a percent. Yes, equals 20. Alright. So, this equals 20,000, right? That's the amount we want to reach. Correct? Our principal is 12,500. Our starting amount times e to the RT. Now be careful with R. What do I plug in? 0.07. Okay, remember it's a percent. If you plug in 7, you're doing 700% interest. Okay? That would be wonderful, but that's not the problem, okay? It'd be wonderful if it's an investment. If it's a loan, we'd be in trouble. So. Alright. Alright, so here we have our formula set up. So how would we go about solving?
Well, first you divide it by 12.
Good. Before you do anything with logarithms, get the exponential part by itself. Okay? We're going to divide by 12,500. And that gives us e to the 0.07 t equal to, what was it? 8/5. So 1.6, right?
You keep the natural.
Alright. So everyone understand what we did so far?
If you
Okay.
put log base e into a calculator, but not like as a natural log, would it still do the same thing?
Yeah, I think it would work. If you have the inspire, and you put e down there in the base, yeah, I think it would work. It should work. So, alright. So now we're going to take the natural log of both sides. Okay? So we have 0.07t. That was the whole point, is to undo the exponential and return just the exponent. Okay? Well, what does that come out to, though? Natural log of 1.6.
It's a small number,
A very, very small number.
pretty much.
Okay?
0.47, pretty much.
Alright, so 0.47 and so on. Alright? Now, when you are solving this, do not round on your calculator at this point. Okay? It's okay to just write down 0.47, but leave that whole number in your calculator, because then we need to finish solving for t. We divide by 0.07, and t equals, what is it, 6.714, okay, 6.71, there's our three significant figures. Alright, and that would be
6 years.
years, okay? So 6.71 years.
Sorry. 7% is
So-
pretty big, actually.
7%?
Yeah.
Depends what you're investing in. If it's a money market, that's a pretty good money market account. If it's a mutual fund, that's a pretty lousy mutual fund.
Banks, no.
If it's a
Most
bank
of them
account, that would be wonderful, but
Yeah.
a savings
Maybe like
account,
3 or 4.
you'll get like, well, no, a savings account, you're lucky to get 1%.
1?
Yes.
Yeah.
On a regular savings account, yes.
Not continuous, this is continuous.
My country, you get
But-
Normally it's not, is it
Well,
continuous?
banks also normally do monthly,
Yeah.
okay? Banks will also normally do monthly compounding.
Money with it.
Okay. But does everyone understand the concept here? Setting up the equation and solving using that inverse, using the inverse of the exponential, which is our log, with the same base. Yes.
Like I always used to get confused with this. When to use the natural log, when to use the log.
Well, it depends on what your base is. Okay. If your base is e, you use the natural log. If your base is anything else, you're going to use the other log with that same base.
Okay.
Okay. And in fact, let's do this same problem, but let's do it compounded monthly.
Is it RT
All right.
or NT?
It might be.
So here.
Are we gonna have a problem like that on the quiz?
What if it's compounded monthly? All right. Well, we have a slightly different formula. Does anyone remember it? One plus
R over N.
r over n to the
Nano
tn power. Okay. Don't forget the p in the front.
How many years was it?
Okay. Well, we should. We're solving for the number of years. Okay. But what if it's compounded monthly? All right. We're still going to plug in the 20,000 for A of t, the 12,500 for our principal, and the 0.07 for the r. Okay? So here's 20,000, 12,500 times 1 plus 0.07 over n,
Well,
which is 12, good, to the 12t power, okay? Because here's what we're doing, remember? We're converting this annual interest rate to a monthly interest rate, okay? And we're converting our years to months by multiplying by 12, okay? Now, we'll follow the same strategy we did before. We're going to get this exponential part by itself by dividing by 12,500. And we've got 1.6 equal to 1 plus 0.07 over 12. Okay?
12.07. 1 point.
It's-
multiplied by 12.
1.0058.
Just one.
Okay, 1.0058
Let's calculate.
to the 12t power, okay? So,
And I do log.
here's the thing.
Yeah.
Leave that number in your calculator. For accuracy's sake, leave that whole number in your calculator because now we're going to do a log on both sides.
1.0.
And what's the base going to be?
It's gonna be
1.00583.
Yeah, okay? That's the base. 1.0058. Now we haven't learned the change of base formula yet, so somebody with an Inspire where you can plug in a
helps.
different base.
You get the end result after you divide by t by 12 should be 6.7339.
Okay, what was it before we divided by 12?
80 point something.
It's 81.2699.
Good.
Okay, then you divide by 12, and what'd you get there, Jacob?
6.7339.
80.5.
Okay, and again, that's years. Alright, so in this short of a time span, compounding continuously versus compounding monthly didn't make a huge difference, although it was a little bit faster, maybe a couple of days. Let's see, 2/100ths of a year would be about 6 days, 7 days. So
Better do a month.
maybe a week earlier we could get our money compounding continuously. But anyways, here you see the basic process. You get the exponential part by itself, and then whatever this base is, we're taking the log with that same base. Yes, Alex?
Is compounding continuously ever smaller than like compounding monthly?
Not if everything else is equal.
It won't make
Where it
sense.
becomes a little tricky is, okay, would it be better to get compounding continuously at like 6.8% or compounding monthly at 7%? You know, a lower rate, and what it comes out to is on a shorter period of time, the higher rate's better. But as you go on, there's an even point, and after that, the compounding continuously will be better.
Depends on how long.
So it's graphs.
So, yeah, yeah.
It's graphs. One
So.
goes,
Mr. Hickson, your clock is working.
It is working. I don't think it's not correct yet,
Yeah, but it's still working.
but it's at least working. So,
It's an hour, like.
yeah.
in advance.
All right, so let's use some time here. I gave you some to practice with.
Can you post those on your website?
What?
No questions to ask us?
It was on the PDF?
No,
Or did I not upload the PDF yet?
No, not yet.
Oh, okay. Okay.
But when you're done.
So, alrighty. So we're gonna take some time here in the last, what do we have here? 10 minutes. I want you to get with somebody right now and work on this, okay? For the last 10 minutes. And tomorrow we'll take questions and then build off of that, okay?